There we go.
There we go. Okay. So thanks to Kirill for asking me to come along and talk. I'm going to carry on the story that Kirill was explaining to you yesterday. I should say that various parts of this are joint with Dmitry Panov at King's and with Kirill. And yeah, this is a kind of conversation that's been going on for a very long time between the three of us. So what I want to say today is a kind of four-dimensional version of what Kirill was explaining yesterday. So I'm going to begin by telling you how you can parameterize Riemannian metrics in 4 dimensions using connections. Then I'm going to explain how to find an equation for the connection which tells you that the metric that corresponds to it is Einstein. And in the course of that, I'll also explain an action on the space of all connections whose critical points give exactly this equation. So it turns out that this action isn't unique in some sense. There's a whole family of actions which all have different critical points, which give you a way of kind of generalizing Einstein's equations. And inside this family, we'll see this one that Kirill mentioned that has very nice properties. And maybe I'll say a couple of things about this other action. And then if there's time, I want to talk a little bit about kind of 6-dimensional interpretation of this story. So these connections, they're not just potentials for a 4-dimensional metric, they're also potentials for a 6-dimensional symplectic form. And there's an interesting side of the story there, but I don't know how much time I'm going to have. So, okay, so let's start. So, I don't know what everyone's background is. There's quite a lot of sort of little tricks in linear algebra in 4 dimensions that I don't even notice when I use them anymore. So if I say something that you haven't seen or heard before, just say and I'll explain it. Okay, so we're going to start. Just going to start with a basic remark about Einstein metrics in 4 dimensions, which is probably familiar to everyone. So if I start with a Riemannian 4 manifold and an orientation, then the 2 forms split into self-dual and anti-self-dual parts. So this is a rank 6 bundle and it splits into 2 rank 3 bundles. And the significance of this from the point of view of Einstein metrics is the following. So the metric gives you a Levi-Civita connection, which you can think of as then giving you a connection on the bundle lambda plus. Okay? So you have the Levi-Civita connection in lambda plus, and now I can look at the curvature of this connection and I can ask what's its anti-self-dual part. Okay? So this is an anti-self-dual 2 form with values in endomorphisms of this bundle here. So if you look at these 2 bundles, they're both rank 3, their product is rank 9. So this is a sort of 9 components of the curvature tensor, and that's the same as the trace-free Ricci curvature in this dimension. So this is essentially trace-free Ricci. So in other words, in 4 dimensions, Einstein's equations are the same thing as asking for the Levi-Civita connection to be a self-dual instanton. Okay, so G is Einstein if and only if this connection on lambda plus is a self-dual instanton. So here, self-dual, just these forms are self-dual, these forms are anti-self-dual, and for a connection to be a self-dual instanton, it means its curvature lies entirely in the self-dual part of the 2 forms. Okay, so what this means is that the Einstein metrics are kind of hidden in the following set. I can look at the set of all pairs CA, where C is a choice of conformal class and A is a C self-dual. Instanton. So I should just say that this splitting of the forms here, although I started with the Riemannian metric, in fact, it only depends upon the metric up to scale. Okay? The Hodge star in middle dimensions is conformally invariant, and so really I only care about the conformal class of this metric. So somewhere hidden in this set curly I are all the Einstein metrics, and the idea of this connection construction is how to look at connections and recover from them the conformal class that makes them into an instanton. Okay, so here's the key definition. I mean, so let me just write it down. Okay, so an SO3 connection A in the bundle E is called definite if its curvature solves some inequality So whenever I take a pair of tangent vectors which are independent, so they span a tangent 2 plane, I want the curvature on that 2 plane to be non-zero. Okay, so these connections are as curved as they can be. Okay. So the point is that I'll explain in a minute, these connections, they single out a unique conformal class that makes them an instanton. Okay. So why is SO3 special? It's special because you're wanting to use the connection to discover this rank 3 bundle. So you need 3 curvature 2 forms. Okay? So I just want to say a little bit about the history of this definition. I've been speaking about this definition probably on and off now for about 6 years, and every time I give the talk in a different department, I discover that the definition is even older than I thought before. So it seems now to be the earliest instance of this definition was something much more general, discovered by Alan Weinstein in the 60s, called fat connections. I mean, these are the opposite of flat connections. They're as curved as they can be. The definition was then rediscovered in a different form by Reznikov in the 90s, and then again by myself, Dima, and Kirill more recently. But these have actually been around quite a long time. Okay, so now let me explain how to find this conformal class. And to do that, and to make life easier for later calculations, I'm just going to need to say a little bit about the linear algebra of lambda 2 in 4 dimensions. So if I take a pair of 2 forms, I can wedge them together and get a 4 form. Like this. And this is a symmetric bilinear pairing on 2 forms. And it turns out that it's non-degenerate with signature 3-3. Okay, so one of the ways to see this is to look at what happens to self-dual and anti-self-dual forms if you pick a metric. And then if you wedge 2 self-dual forms together, you get the volume form times their inner product. And for anti-self-dual 2 forms, you get minus their inner product times the volume form. So this wedge product is positive definite on lambda plus and negative definite on lambda minus. Okay? So there's a kind of converse to this statement. If I take a 3-dimensional subspace inside lambda 2, so if V is a 3-dimensional subspace inside lambda 2, on which the wedge product is definite, then there exists a unique conformal class and orientation such that V equals lambda plus. Okay? So this is, I don't know, once you've been playing with 4-dimensional metrics for long enough, this is something that just becomes an automatic statement. But one sort of naive way to see that it should be roughly correct is that the space of definite subspaces has the same dimension as the space of metrics up to scale. They're both spaces of rank 9, of 9 parameters. Okay, so to give a conformal class, I just need to find this definite subspace, this V3. Okay, so now let me explain how to do that given a definite connection. Okay, so to make life easy for myself, let's just choose a local frame EI is a local frame for E, an oriented orthonormal basis at each point for the fibres of E. And then I'm going to use the same letters. Okay, to begin with, let me use a hat so that we can see that they're different. This is generator of rotations about EI. So this is a frame, a little s over B. Okay, make sense? So I've got the x direct, I've got my 3 coordinate directions in E, and that gives me 3 rotations generating little s over B. And then I can write my curvature FA as 2 forms with values and rotations. So these FI are just 2 forms. And now it turns out that the definition of being definite that I gave up here is equivalent to the following fact. So A is definite if and only if the span of these FIs inside lambda 2 is a definite subspace. For the wedge product. Okay? So these connections are exactly the one whose curvature 3 forms completely span a definite subspace, which means that there's a unique conformal class that will make a definite connection an instant on. Okay? Because it's the one whose self-dual forms are exactly the FI. So there's a unique conformal class CA such that A is a C self-dual instanton. Okay, so this tells you how to go from a definite connection to a conformal class, and what we want is an actual metric. So to get from the conformal class to the metric, we need to pick a volume form, and then we need to see, once we've done that, is this guy here actually the Levi-Civita connection of that conformal, of that metric? Because that's what we're looking for. We're looking for a metric whose Levi-Civita connection is a self-dual instanton. Okay? So the story of the volume form is a little bit involved. So let me just avoid it at this point in the talk, and we're just going to pick one arbitrarily and see what happens. So just for the next 5 or 10 minutes, let's just pick an arbitrary volume form and see what happens. Okay, so what we want to ask is when is A the Levi-Civita connection of GA? Okay, so the first thing to notice is that these 2 connections are connections on abstractly different bundles. Okay, A is a connection on our auxiliary bundle E that I wrote down right at the very beginning before any metric existed. Okay, whereas the Levi-Civita connection, at least for what I'm talking about here, is a connection on lambda plus. And these are, so this is a connection on E, and this is a connection on lambda plus, and these are different bundles. Okay, so in order to ask are they the same, I need to identify these bundles. All right. Now there's an obvious way to identify them because I've chosen a basis. Given a basis for E, I get a basis for lambda plus, given by the curvature forms. Okay, so naive way to identify E and lambda plus is via the curvature. So I just take this frame, EI, and I send it to the curvature forms, FI. Okay? And now I can ask, once I identify these two bundles in this way, do the connections match up? But there's immediately something that can go wrong, which is that this map is not an isometry between the bundles. Okay? So A is going to be a metric connection on E, and nabla is going to be a metric connection on lambda plus. So if I want them to match up, I really ought to use an isometry here. Okay? And in fact, this isn't an isometry precisely because these two forms are not an orthonormal basis. Why should they be? Okay? So if we look at this matrix Qij, which is the inner products of these curvature forms, which is the same thing as taking their wedge products and dividing by this volume formula I chose, this guy needn't be the identity. It's just some positive definite matrix. So this arrow is not an isomorphism, not an isometry. So if I use this to think of, for example, A as a connection on lambda plus, I'm not even going to get a metric connection. Okay? So what I need to do is I need to twist this map, twist this arrow by something which undoes the fact that the F's are not orthonormal. Put another way, I need to do Graham-Schmidt on the Fi's to turn them into an orthonormal form. Okay? So there's a kind of canonical way of doing that. So I'm going to write phi I to be, I take Q, I take it to the minus 1/2. So Q is a positive definite matrix, so it has a positive definite square root, which I can then invert. And this linear combination of the F's now gives me an orthonormal frame for lambda plus. Okay? And these are the guys that I should use to identify E and lambda plus. Okay, so I can write down this new gadget, phi A, which is Q to the minus 1/2 of the curvature of F. And then this sends EI to phi I. And this is an isometry. Okay? So now I'm going to use phi to compare A with Levi-Civita connection. Okay, so they're both metric connections on lambda plus, but of course there are lots of metric connections on lambda plus. How do I single out the Levi-Civita connection? And it's determined by the fact that it has vanishing torsion. Okay, so let me give you the four-dimensional analog of that. Okay, so maybe you're more familiar of seeing the torsion of a connection on the tangent bundle or the cotangent bundle rather than on the bundle of self-dual two forms, but it's just exactly the same thing. You take a section of the bundle of self-dual two forms, you take its covariant derivative to get a one form with values in self-dual two forms, and then you skew over all of the indices to get a three form. Yeah, so this is connection. Let's say D. So an arbitrary connection D. I take the covariant derivative with respect to D, and then I skew. Let's call this operation sigma. So then I look at sigma done after D, and I compare that to the ordinary exterior derivative. Okay? And this is the torsion of the connection D. So if you replace the lambda plus with lambda 1, you'd end up in lambda 2, and this is just the torsion that makes sense in any dimension. And now we have another kind of fundamental lemma of four-dimensional Riemannian geometry. whose proof is essentially the same as the characterization of the Levi-Civita connection in all dimensions. So the Levi-Civita connection is the unique metric torsion-free connection on lambda plus. Okay? So, to see if A is the Levi-Civita connection, we just need to compute its torsion. Okay? And so let's see how to do that. So the torsion of A, thought of as a connection in lambda plus via phi, is, so obviously this torsion is going to depend upon phi. Okay, I could have taken, there are lots of different isometries between these two bundles. I could have twisted phi by any gauge transformation of E, and then I'll get a connection with different torsion. But I've chosen to use phi. So phi is going to appear in the formula, and the torsion is given simply by taking the covariant derivative of phi A, the coupled exterior derivative. So phi A, if you look at it, is a 2 form with values in little so of E. Okay, so this guy is a section of 1 forms with values in little so of E, and this bundle is isomorphic to 3 forms with values in lambda plus G, which is where the torsion lives. See, the torsion eats self-dual 2 forms and gives me 3 forms. That's the same space up to isomorphism as 1 forms with values in rotations of E. Okay, so out of phi, I can cook up a natural object that lives in the right space to be the torsion, and it turns out that they're the same thing. Okay? So this is the torsion of A. Make sense? At least in principle.
Can you explain why you write the star? Yeah, why it's not
Okay, so this is kind of pedagogical. So phi is actually a self-dual 2 form, you see, because by definition the f's are all self-dual, and I've taken a linear combination of these self-dual 2 forms. So d of a self-dual 2 form vanishes if and only if d star vanishes. So it wouldn't matter whether I put the star there or not. But the reason that I put the star there is to remind you of the Yang-Mills equations. So let me write the next result, and then I'll... So, proposition, if dA star of phi A equals 0, GA is I star. So before I come to that comment, let me just say one thing. So already this is actually there's something about this equation that tells you you're doing something a little bit subtle, which is the following thing. So this equation, so let me write it out. It's dA star of q to the minus a half of f of a. Okay, so this is the kind of equation we're looking at. So the reason the star is in here is to make this look like Yang-Mills equations with a twist. Okay, so the Yang-Mills equations would just be this. All right, but they're satisfied automatically because A is an instanton. Okay, so that just becomes the Bianchi identity. Okay, so the next thing to notice is that just like Yang-Mills equations, this equation is second order in A. Okay? And this is somehow a small miracle, because if you just naively compute the Ricci curvature of G, okay, so the connection A gives the curvature which is first order in A. Then if you look at G, it's algebraic in the curvature. Okay? So the curvature of G is third order in A. So if I just naively wrote down the Ricci tensor of G, I'd get a third order expression in A, which I set equal to 0. That's a different equation. But this one turns out to imply it. Okay? And it's a little bit like what happens in Kähler geometry. So in Kähler geometry, you have a Kähler potential, and the second derivatives of the potential give you the metric. So if you were to naively compute the Ricci curvature, you'd get a fourth order equation in the potential. But in fact, there's some magic that happens, and it turns out to be a second order equation in the potential. Okay? So this kind of gain in derivatives tells you something interesting is happening. So it's second order in A, not third order, as you might expect. Okay, so now I want to point out one more analogy with Yang-Mills, which is the following special case of this equation. So, as I already said, in 4 dimensions, the Yang-Mills equations, the second order PDEs, they're implied by the connection being an instanton, which is a first order PDE. And the same thing happens here. There's a first order PDE which will imply this one. Okay? And that's the following. So, if you remember when I was discussing this map between E and lambda plus, we had this matrix Q, which was my wedge products of the F's divided by my arbitrary choice of volume form. What happened if this really was the identity? Okay? Suppose this equaled the identity. So if Q equals the identity, then phi A is equal to FA, and then dA star of FA equals 0 because A is an instanton for my choice of conformal class. So this equation, Q equals the identity, is first order because it just depends upon the curvature and no derivatives of curvature. Okay? So there's a first order equation which implies the second order equation. So this is the analog of instantons are special solutions to the Yang-Mills equations. And now you can ask, what does this imply for the metric? Okay, so in this case, the metric is what I guess physicists call an instanton. In other words, it's not just Einstein, but the anti-self, its Wahl curvature is anti-self-dual. So if Fi wedge Fj is delta Ij times mu for some volume form mu, then Ga is anti-self-dual and Einstein. And in fact, it has non-zero scalar curvature as well. Okay, so I should say, in the exposition as I've given it, I've kind of hidden the fact that these Einstein constants, they're always non-zero. And that's related to the fact that this, if you think of flat space, all the F's vanish, okay, for example. So we need the F's to give you an isometry between, or an isomorphism, they need to span lambda plus. Okay, so I've hidden the hard part, which is finding this volume form. So it turns out that you shouldn't just be picking, really, as I've explained things so far, this equation is not just an equation for A, because to define Q, I needed mu. So far, this is an equation for A and mu. But it turns out that there's only one choice of mu that will ever work, more or less. And so really, you can interpret this as just an equation for A. And I now want to explain how to find the volume form. Okay, so there's already one situation in which we know how to find the volume form. If we're in this happy situation where the wedge products of the F's is the identity times some volume form mu, that's the one we should take. Okay, so first naive guess. For our volume form is, I don't know, mu equals 1/3 the trace of FA wedge FA. So FA wedge FA, this is an endomorphism with values in 4 forms. I take its trace, I get a 4 form, and that's the 4 form I want to use. And if I did that in this case, I get exactly mu. Okay? So this is up to some scale. This is the first Pontryagin form of A. Okay? This is the guy whose integral gives you the first Pontryagin number of the bundle E. Okay? So for quite a while, Dimitri and I worked with this volume form, and then when we met Kirill, we realized that we shouldn't have been. Okay? So here's how to escape this problem. So this is great for the anti-self dual Einstein metrics. It works perfectly, but it will miss the other Einstein metrics. Okay? So it doesn't work for general Einstein metrics. So there are lots of different ways to reverse engineer the right choice, but rather than go through that, what I'm going to do instead is I'm going to describe the action which makes use of the volume form, and hopefully I'll be able to explain how the whole story fits together. So, idea. Find volume form. So that total volume is an action for the theory. Yeah, so I want to choose this volume form in such a way that when I write down the total volume of the manifold, the critical points of that action functional are exactly this equation up here. Okay, so let's begin. Since we don't know how to make a choice, let's make lots of choices all at the same time and then work out how to restrict ourselves to the right one. So let's take P, a section of symmetric endomorphisms of E. Symmetric endomorphisms of E, which is positive definite. And for each choice of one of these, I'm going to get a volume form. So I'm going to write down mu of P and A to be the trace of P to the minus 1 FA wedge FA. See, if I took just the identity map, this would be up to some constant first Pontryagin form. Okay, but now I'm allowing myself to mix up the 4 forms in this endomorphism valued 4 form by multiplying with P to the minus 1 before I take the trace. Okay? And now I have a whole family of volume forms parameterized by these sections. Okay? And so now I can look at sort of a kind of combined action, which is the total volume of this guy. And I can try and study the critical points of this, see what happens. Now the first thing to notice is that this guy's critical points are not going to, that there aren't going to be any, because I can just scale P by a constant, make it bigger or smaller. That just scales this volume form by a constant, making it bigger or smaller, and so I can just change this into, I'm never going to have a critical point. Okay? So I need to get rid of the scale invariance for P. Okay? And this is what leads, in fact, to there being a whole collection of actions, one of which gives you Einstein's theory. And it's how you make this choice to get rid of the scale in P. So let me explain how to do this. Okay, so I'm going to write curly P is the set of positive definite 3x3 matrices. And I'm going to write curly C inside curly P. This is going to be a hypersurface which is invariant under the action of SO3. Conjugation here, I mean. Invariant hypersurface. So two examples that are going to be very important for us will be trace of p equals 1 or determinant of p equals 1. I guess maybe I should put trace of p equals 3 here because I'd like the identity to be in there. Okay?
But you can trace square root of p.
No, you'll see, it'll come out. Right, so because this guy is SO3 invariant, I get a corresponding subbundle of the space of symmetric endomorphisms. Okay, so then I have this kind of C of E subbundle of endomorphisms of E. And now I can look at this action, and instead of trying to extremise over all P and A, I want my P at each point to lie in here. In other words, I only try and extremise over P's that have constant trace or that have constant determinant, for example. And there you can see that I've stopped this scale change in P. Okay, so restrict to P being the section of C of E. Okay. Okay, so now let's just take the variation of mu with respect to p. So if I differentiate my action in the direction of p, so x is now just some arbitrary symmetric matrix, 3 by 3 matrix. I'm varying s in the p variable, then I get minus the integral of the trace of p to the minus 1 x p to the minus 1. And then I'm supposed to multiply by this f wedge f. So let me just stick to the notation I had before. So here I've chosen an auxiliary volume form just to make my calculation easier. So FA wedge FA is just some endomorphism valued 4 form. Okay, I've just chosen a reference 4 form. So mu is a reference volume form. So Q doesn't have any intrinsic meaning except up to scale. If I chose a different reference volume form, I'd just be scaling Q. Okay? So now let's look at what this formula says, and so I'm taking the inner product of x with q, but I'm kind of twisting them by p to the minus 1. So this is a familiar formula. In general, this is how you would write down an inner product on the tangent space of curly p at every point. Okay? So if I look at curly p, the positive definite 3 by 3 matrices, there's a natural inner product. So xy at the point P is this trace p to the minus 1x, p to the minus 1y. And this actually makes this space P into a non-positively curved symmetric space. So this is, if you like, the natural Riemannian structure on P. Okay? And all I've done here is I've taken the L2 inner product between x and q using my volume form mu. Okay? So this is like minus the L2 inner product of x and q.
I'm really stupid. I think I just missed something. Where did this x come from?
X is just the variation of p.
Ah, sorry.
It's delta p.
Yeah.
Yeah, it's okay. I realise that at some point mathematicians' notation diverges from physicists' notation and convention.
I think I just,
Yeah, we call it delta p, you see.
You'd call it delta p.
Yeah, but no, sorry, don't.
Okay, so, or p dot. Sometimes mathematicians, okay. So x is the variation in p, and this explains why I put the p to the minus 1 in the original formula, so that I would get this out, rather than just trace x, q. Okay? So we're seeing the natural Riemannian structure of curly p appear, and the variation of the action is just this L2 inner product, and so obviously it vanishes precisely when q is orthogonal to all the x's. Okay, so what that says is that Q needs to be normal to the tangent space to C, i.e. ds dp vanishes if and only if Q is normal to the tangent space to P, to this hypersurface C. Okay? So now let's see what happens when we look at trace of P equals a constant. So let me work this example out. So if C equals trace, is the set trace P equals 1, then the tangent space to P is of course trace X equals 0, and the normal vector is P squared. Okay, because I've got two P to the minus 1s in here before I take, if I had P squared here, this would just be trace of X. Okay? So I need Q to be proportional to P squared, which is what you were anticipating with your square root. Okay? So okay, so to solve the Euler-Lagrange equations for just varying P, we should take P squared to be proportional to Q. Okay, remember Q is only defined up to scale, and I just need Q to be normal. It just needs to be some multiple of the normal vector. I've just chosen P squared. And how do I fix this scale? Well, I know that the trace of P has to equal 1, because that's my condition here. So the scale determined by trace P equals 1. So this completely determines for me what P should be. Okay. So now let me convince you that the full Euler-Lagrange equations are exactly that second order PD that I wrote down before. Okay, so now we can really fix our choice of mu. So fix mu A such that Fa wedge Fa equals Q times mu A, where the trace of Q to the half equals 1. Okay, you see, if I double mu, that halves Q. Okay, so by changing the scale of this mu, I can arrange for the trace of the square root of Q to be anything I want, and I'm going to choose that scale so that this matrix has trace 1. Okay, then if I take P equal to this square root of Q, this solves the first Euler-Lagrange equation, and now I need to vary with respect to A. So if I look at the change of the action, so here little a is delta capital A. So I look at the variation here, what do I get? I have the integral over the whole of M of the trace of P to the minus 1, I guess a 2 might come out, dA A wedge FA, which is up to some constant, the L2 in a product of dA star Q to the minus the whole FA. And lo and behold, we've got the right equation. Okay, 10 minutes left. All right, so this action we can integrate out. We can solve first for P, because we know how to do that algebraically. If you look at the action, it doesn't involve, I've wrote the action out, so, but it doesn't involve derivatives of P. So you can just algebraically solve for P. And once you've done this, what's left of the action is actually total volume. So let me write that down. So let S trace of A be just the integral of this mu A. So here mu A is chosen so that F wedge F is Q mu A, where the trace of Q to the half is 1. So this is the magic rule for choosing the scale. And this is just the action that I originally defined where P is Q to the half. So remember, I had an action which depended upon a matrix valued function and a connection. I now tie the matrix valued function to the connection by this rule here to set Q, and then I take P to be the square root. And then if I take the integral of that volume form, it turns out to just be this. Okay? So this is a total volume, and this guy here, the critical points of this guy are exactly the same as this one, which give me the Einstein equations. So STR is a pure action function, a pure connection action. Using Einstein's equations. So I just want to make one more comment about this action before I move on to different actions. So earlier on I was trying to persuade you that there are analogies with Yang-mills. So one of the features of Yang-mills in 4 dimensions is that the action has a non-trivial lower bound. Okay? If you look at the L2 norm of the curvature tensor of a connection on a 4-manifold, it's bounded below by some multiple of the first contrarian class. And this bound is attained precisely for instantons. And the same thing happens here. So, you kind of, once you know what you're trying to do, it's a fairly straightforward lemma. This action, this total volume, is smaller than some topological number, which is 3 times the signature of the manifold plus 2 times the Euler characteristic. Okay, so there's a topological bound, and it's attained if and only if this matrix Q is actually the identity. So again, the topological bound is saturated precisely for this first order solution, this solution to this first order PDE. So you should think of this as being the analog of saying Yang-mills action is bounded, the bound is attained precisely by instantons. Okay, so in the last 5 minutes, I want to tell you just a little bit about different actions. So here, in this game here, we were looking at the set curly C, where the trace of this matrix P is just equal to 1. But there are lots and lots of different choices of hypersurface. By varying this 5-dimensional hypersurface inside the 6-dimensional space of positive definite matrices, I get different actions. These critical points will be deformations of Einstein metrics. And yesterday, Kirill mentioned a seemingly more attractive action from this point of view. And this action, this alternative choice, is just given by taking a different invariant expression for P. C hat. We just take the determinant of P equal to 1. So there are at least 2 reasons to see this as more natural, besides, of course, the fact that this guy gives you Einstein metrics. So really I don't know. That seems very nice from that point of view. Here it's less clear what the critical points should be. Okay? One case of the critical points is still the anti-self-dual Einstein metrics, but the higher degree critical points is not clear what they are. But why is this nicer? That's because this, well, one way of seeing it is that inside this Riemannian space curly P, this is a totally geodesic hypersurface. Okay? And one sees this in so many ways. When you do the calculations, there are lots of things that become complicated when using trace of P equals 1 that become 0 precisely because the second fundamental form of curly C and P vanishes in this situation. So gives different action. Let me just put my notes so that I don't get things wrong. Okay, so here I managed to convert, when I took trace p equals to 1, I converted the action into an action purely on terms of connections. You can do the same thing here, and let me just tell you what the answer is. So this time you take FA wedge FA equals Q mu A, where now the determinant of Q equals 1. Okay, so that tells you how to change the scale of mu. So I scale mu in order that the determinant of Q becomes 1. Then I take P equal to Q, that solves the Euler-Lagrange equations for varying the action with respect to P. And then I get a new action, S det of A, which turns out to be 3 times the integral of this mu A. So it's again total volume. And you have an analogous lemma to this. You have an analogous topological bound. Same Q equals identity when bound is changed. So the kind of the analog of instantons for this action are the same as for general relativity, but the other critical points will be different. And it's not clear to me yet what geometric meaning that they have. So maybe in the last 2 minutes, let me explain a completely different way to find this volume form, which doesn't proceed through the action, which will give you another reason to believe that this is somehow natural. Okay? I mean, I'm kind of bullying you into thinking it's natural just by saying the word's totally geodesic here. Okay, I mean, this is the canonical 5-dimensional hypersurface in curly P from a mathematical point of view. But what's another reason to come up with this mu? And then I'll stop. So anyone who wants to hear about symplectic 6 nanofolds will have to call me afterwards. Okay, so we have these forms. Remember, the curvature is Fi tensor rotations around the EIs. Okay, and now I'm going to write down the metric. Okay, so let me write down the metric. So I'm going to define a bilinear form on tangent vectors u and v. And here's what I'm going to do. I'm going to take epsilon I, j, k, interior contraction down u of fi, wedge interior contraction down v of fj, wedge fk. Summing over I, j, and k. And that's a bilinear form with values in 4 forms. Okay, so this is bilinear form. Now I choose a 4 form, so it turns out that A being definite is the same as saying that this bilinear form is definite. So, notice I can't talk about positive definite or negative definite because it takes values in a line, an abstract line. Okay? But once I know it's definite, that singles out for me an orientation, which makes this positive definite. Okay? Let me just divide by that guy there. So choose any mu such that VA UV divided by mu is positive definite. Let me call this G sub mu. Okay? Now I've got a genuine Riemannian metric. Okay? That genuine Riemannian metric will have a volume form. So G mu has a volume form, d vol of G mu, and I can ask, does it equal the mu I first thought of? Okay? The special mu that makes this equation true is exactly this one. So those of you who are used to G2 geometry, there's a similar game. Instead of a triple of 2 forms, you have a single 3 form. Out of that 3 form, you could have a bilinear form with values in 7 forms. You divide by a volume form, you get a metric. The volume form you should choose is the form mu for which the metric's volume form equals mu. Okay, so this is exactly the analog of what happens in G2 geometry. Will give you this mu here. Okay, so there are 2 completely different reasons to think that this theory should be nicer in some sense than the trace p equals 1 game. Okay? And this is also, I mean, there's a reason why I'm saying the words, this is not just a formal analogy. There's actually an algebraic way of throwing away 3 dimensions in 7 dimensions, turning your 3 form into a triple of 2 forms, and then this really is the same G2 calculation. Maybe just 15 seconds, you can talk about signs of definite connections as well. So notice that I chose my mu so that this was positive definite, but also the f's should have positive square. Is that positive the same as this positive? So that gives you a sign of the connection. But perhaps I'm just saying too much now. Okay, so this is probably a good place to stop.
But these are Einstein as well. But these are not Einstein.
You mean the critical points of this guy?
Yeah.
Well, so this action has a topological upper bound, and when it's attained, you get anti-self-dual Einstein metrics. That's this first order equation.
Otherwise.
But the other ones, no. No.
Is it easy to say what they are?
No.
So mathematically nice, and kind of this construction seems very canonical.
Yeah, it does.
Why does it seem so hard to say what the critical points are?
Partly because I haven't looked that hard. I mean, there's an analogous game you can play. Instead of using curvature forms, you can use symplectic forms. Okay? So you replace the f's with symplectic forms, and then if you play this game, you can write down the action and everything, and then you can prove that the only critical points are hyperkähler triples. So then it really is nice. There are no intermediate critical points. And I wonder, I don't know of any examples of intermediate critical points on compact full manifolds. I don't know, do you know any complete examples? No, they always seem to develop singularities, right?
The examples that we know.
Mm-hmm.
You can imagine, I mean, there's, you could fix, well, I mean, you fix the determinant, the trace, or the trace of the square or something. So you've got 3 parameter family in total. Do you know of any others that actually give Einstein?
Carol will be better.
No, it's nothing else that gives Einstein.
It's just the trace.
It's just the trace, yes.
So you can't write these actions in terms of the metric? Like if you had Einstein, you have square root of g times r?
No, this seems to be very different. I mean, so the Einstein-Hilbert action, for example, is never bounded.
So what is it?
Who knows? It's complicated because the metric, I mean, the curvature tensor is 3rd order in the connection, but this action is 1st order in the connection. So it's not given by local invariance. If you insist on passing to the metric, you can't then recover this because you have to solve some 3rd order differential operator. It looks non-local from the metric point of view.
You think it's non-local?
No, from the metric point of view, it would be non-local.
In terms of the metric, it's
Yeah.
non-local action.
It looks non-local.
Yeah. Another explanation of what this action is, think about the 1st order formulation of gravity, where you have independent connection and a metric. If you integrate out the connection, you get back the Einstein-Hilbert action, but you can also, as I explained yesterday in the case of 3D, you can integrate out the metric. Because in the 1st order formulation, the metric enters action algebraically. If there is a non-zero cosmological constant, you can integrate out the metric. This is like, well, Polyakov action for string theory, where it's the same trick, right? You go from non-Bogota to Polyakov by integrating out the metric. So the same you can do in the 1st order formulation of gravity. You can integrate out the metric, and then you get actions of this type. It's the typical form of this action is some square root of something depending non-linearly on the curvature of the connection.
I mean, A sort of plays a dual role here as a sort of a potential for the metric.
Yes.
And you might have connections.
So maybe the right analogy here, these actions are like Nam-Vu-Gotha actions. Square root of determinant of some dx.
Yeah, but those you can rewrite in a covariant way.
These ones you can also write explicitly as non-linear functions of the curvature. In that sense, they're local.
But curvature of A,
Curvature
not
of A,
curvature of
yeah.
G. There. If you
But in the Nam-Vu-Gotha case, you can write it, it's a square root of d alpha x, d alpha
Mhm.
x. Then you can write it covariantly in terms of the x mu sigma. The same variable. You don't have to like go back to some other variable.
This you can also write very explicitly in terms of curvature of the connection. Maybe that I can explain.
but definitely not curvature of the Riemannian metric.
The variable here is the connection, and action depends algebraically on curvature of that connection.
Just really quickly, the case where you do get Einstein extrement, you don't get all
No,
Einstein extrement.
I guess not.
In
Because-
particular ones with vanishing scalar curvature.
You don't, yeah, that's right, you don't get Ricci flat metrics. There is a
Yes,
version of this story which will get you hyperconic manifolds, but then instead of looking at an SO3 connection, you need to look at a U1 cross U1 cross U1 connection. And then these Fs, they become symplectic forms, and in that case, both the determinant and trace actions, they have a unique critical point, which is a situation where the omegas, these Fs have become symplectic forms, and it's the situation where their wedge products are the identity matrix, which tells you that the triple's hypercale. So I mean, there is an analog of the story there. But for Ricci flat 4 manifold that's not hypercalar, I don't know.
And the problem is just these definiteness things that you've needed to.
Exactly, yeah. You're only going to pick up guys whose, in this version of the story, you're only going to pick up guys whose Levi-shifted connection on lambda plus is definite. I mean, at a generic point, if the curvature is definite at one point, it will be definite, morally speaking, away from a three-dimensional hypersurface. So you can play this story with those sorts of connections. I haven't really looked at the analysis, but then you would imagine that you produce the Einstein metric, which will then extend smoothly over these hypersurfaces. I mean, so there are examples where you can look at what happens, where you have genuine Einstein metrics that look like this. And you can see that the equations look like they're going to become singular, where the definiteness fails, because you're dividing by zero. But at exactly the same point, you're multiplying in the numerator by zero as well. And so,
But the Jacobson versions, they were all non-zero cosmological constants as well, weren't they?
No, they were talking about zero cosmological constant case.
That's right. So yours were non-zero.
Yes.
So Ted Jacobson did have pure connection forms with zero.
Zero cosmological constant, yeah.
Yeah, that's
It's
right.
more involved, and it can be really, you can see it as a limit when you take lambda.
You can see it's a little. Okay.
You can see it.
So it just becomes cleaner
Yeah.
when cosmological
Yeah.
constant is non-zero.
So there's the conformal gravity, which is different from Einstein gravity.
The difference, all these gravities, you can explicitly see that they propagate 2 degrees of freedom. You can, for example, do Hamiltonian analysis, you can see that they are about gravitons, and there is nothing else. And of course, this is different from conformal gravity. Conformal gravity has much more in it.
More degrees.
Yeah.
You could imagine restricting just the classical action for conformal gravity to Einstein degrees of freedom, and then that would require a non-zero cosmological constant to get kind of a non-degenerate answer. I don't know. It seems roughly analogous to.
Another useful fact about this other theory of gravity is that you can look at it just to see what it is. You can determine, for example, 3 graviton scattering amplitude. I mean, because you have an action, you can see what the modes are, and then you realize that it's the usual graviton scattering amplitude plus plus minus that we're used to from GR, plus there is a amplitude that comes from Riemann cube. So you also have here all plus and all minus amplitudes. So
This is with the debt theory.
This is for the debt theory.
Really?
Yeah. Debt theory is basically Einstein-Hilbert plus Riemann cube.
So there's a case where you get all plus and all minus.
Well,
3
actually, I'm
point
lying.
zeros.
This theory is because it uses self-duality. It's chiral, so you only get either all plus or all minus, but not both. So it's not Riemann cube, but it's the Weil plus cubed. This is the right way to think about it. But of course, it's just the beginning, right? I'm talking just about the free radical amplitude here. It's so it's not just Einstein plus Weil cube. It's an infinite action in principle, but if you just look at free radical scattering, this is what you get.
And the fact that you're stuck in 4 dimensions all has to do with the fact that you're using instantons to gauge them.
I don't think of it as being stuck. my original motivation was to try and understand 4 manifolds and symplectic 6 manifolds. So it was a tool to solve a different problem.
Is there any version of this that should work for a Lorentzian signature with real metrics?
Yeah, I guess you want to replace SO3 by SL2C. And then impose reality.
Complexify everything, but then
Yeah.
the problem is getting something corresponding to real metrics.
Right, yeah, then you have to find the reality conditions. I mean, Kirill knows more about this than me.
There is some simple reality condition. Well, basically, the reality condition is that your Lorentzian metric should be real. That's the reality condition, and it works. So
But
you
it's
can-
not. Yeah, I guess you can't really say it directly on the A, can you?
But then what is the
You say it on the
topological
F.
bound that you get?
You can say it on the F.
The reality condition is that f, which complex conjugate f, is equal
Oh
to
yeah.
0.
Okay.
That's the reality condition.
Is there still a topological bound for Because there are no non-trivial instantons in those.
I guess not.
And the trivial one you have is precisely in this class that you can't describe because it will be vanishing.
So you could also do this in signature 2 too, presumably.
Yeah, signature. You can,
SL2 and
then it's just
SL2.
SL2R connections. Yeah.
But then I guess you lose the positive definiteness in every step. Those square roots start to become more awkward, I guess, if you're not positive definite.
Just another comment. When solving Einstein equations in this formalism, you see that the square roots that you have to take are not necessarily positive definite. You need to allow other branches of the square roots. It becomes essential. You can see it, for example, just by taking the solution of Einstein equation and determining. So, for example, you take black hole solution with non-zero cosmological constant, and you see what is what there. And you see that you need other branches of the square roots. So
Right,
this
yeah.
matrix square root of q is not necessarily positive definite.
I mean, you just needed p squared equals q. You didn't have to take the positive definite square root. So I guess in the example you're talking about there, well, the one I know better is the page metric. Sort of the page metric on the blow-up of CP2. In one part, you want to take the positive square root, and then 2 of the eigenvalues become 0 of this Q on this hypersurface where it stops being definite. And then on the other side of this hypersurface, you want to take positive and then 2 negative terms in the square root.
I see.
If you take the wrong sign, you just get the same metric doubled, which doesn't extend smoothly.
Okay.
There is another even more interesting example.
And that's positive. That's a Euclidean metric, so
It's a Riemannian signature.
it's a Riemannian signature. Yeah.
There is another example if you take the asymptotically hyperbolic situation. So lambda is negative, asymptotically at infinity, you have asymptotically hyperbolic, so asymptotically in instanton. I'm not saying this is the black hole metric that I'm talking about. And then there is a surface in this space where just one of the eigenvalues changes sign. So actually your connection goes from negative definite to positive definite, which is this is very interesting. This is what it does in the solution.
I have
more of a physics question. So you said that these actions are they are not local if you try to write down in terms of the metric, right? So
They can't be. They're first order in A, so
Right.
they're zeroth order
So-
in G.
I don't know if you looked at like, loop amplitudes or specifically they are normalized. What kind of operators can you add?
Yeah, you can do all this. Of course, these theories are non-normalizable for exactly the same reasons as GR. Basically, as soon as you start expanding around the background, these
Right, so it's not
dimensions.
like you will find that so that's finite, right? Because
No.
of this.
Thanks, Georgie.